Hi everyone, I'm Brian Litz. Today we're going to talk about WEZ, Weapon Employment Zone. It's a new feature, a new capability in ballistics, and we're here to explain what it is, where it comes from, and how you can get the most out of it. Okay, what is it and where it comes from? We're going to get into that. The shooting applications like calculating your hit percentage under defined field uncertainties, that's going to be a big part of this. Like, you immediately are going to start seeing hit percentages with WEZ, but it's very important that you know what's driving that percentage. You're defining the uncertainties that create this calculation, and it's important to understand what those inputs are and how they're used. Just like the inputs that you get your elevation and windage with, you know that it's garbage in, garbage out. You give it the wrong inputs, you get the wrong outputs. It's no different with WEZ and how it affects your calculated hit percentage. And I'm also going to show an example of setting up a WEZ in AB Quantum, show the target selection and setting the different field variables that I've been talking about. All right, let's get into it. I first was introduced to, became aware of WEZ when I worked for the Air Force. They have weapon employment zones for pilots that characterize the performance of their weapons, so that you can tell, like, am I in the zone where he can shoot me and I can't shoot him, or the other way around? And so having an awareness of your weapon's performance, especially in a dynamic engagement like air-to-air combat, the WEZ is a very important thing for the pilot to be aware of, and it's what I worked on. So I had this in mind as a shooter. And in 2009, I wrote the book Accuracy and Precision for Long-Range Shooting, which is really where WEZ was first applied to long-range shooting. And in that book, I break down the approach that we use to calculate WEZ. We're, instead of looking at dynamic air combat here, we're looking at static targets on the ground, but the conditions of the environment are what give you the uncertainties that drive the hit percentage. So for example, if you have a lot of uncertainty in wind, you'll have a lower hit percentage than if you have little uncertainty in wind. And wind, range, muzzle velocity, all these things are uncertainties that you get to define, which go into how your group is affected. The very first software that we had with WEZ in it was AB Analytics for PCs. That came out in 2013, 3 or 4 years after the book. Then it took quite a few more years to get WEZ integrated into field devices, but just this past year, 2024 and now 2025, we have WEZ in the Leica binoculars, and also the Kestrel has a WEZ version also that will calculate this on board. But most of what I'm talking about in the examples are going to come from WEZ in AB Quantum app. That's probably the thing that most users are going to encounter WEZ, so that's what we're going to go with. Okay, so now that we've done a quick overview of like what is WEZ, where did it come from, what are we doing with it, we're going to get into a little bit more of the details now. So this graphic shows you like the concept of how WEZ is calculated with range, right? You've got the same size target, and as you go out in range, you can see how the group size opens up. It's 100% for a while, but then you get to a range where you start having some shots miss the target due to the dispersion that's driven by the field variables that you define. And in assigning a hit percentage at every range is what the WEZ is doing. And it assigns that hit percentage by literally counting how many of the simulated shots are on the target and how many are off the target. And those simulated shots are shots that are all run in a ballistic solver. The trajectory is run, and applying, drawing from the pool of uncertainties that you give it. That's why there's dispersion in the shot group. Okay, and it's just a matter of how that dispersion compares to your target size that gives you your hit percentage. This is a typical way to show a WEZ result, is in a plot like this that shows you how your hit percentage drops with range as you go out. In this example, it's 100% through 600 yards, and then drops to about 50%, beyond 1,200 yards. So, it's giving you a number in a tabular form for your hit percentage at all ranges. Another way to have a result from WEZ is to show it in the context of a target, an animal that you're hunting, or say a steel target in a match. And here you can see what your dispersion would look like before you take a shot in those conditions, assuming that you define those conditions correctly in the solver to begin with. So let's do an example, just a quick look at the kind of analysis that you can do with WEZ and the kind of things that you can learn. So starting here, we've got a setup. It's a 6.5 Creedmoor at 1,000 yards on an IPSC target. And we start out with a wind speed uncertainty of 2 miles per hour, and you can see what the shot dispersion looks like. That gives you a 47% chance of hitting the target in those conditions. Now, if we cut the wind uncertainty in half from 2 to 1 mile per hour, you can see how that group narrows up. It's not as wide anymore, and your hit percentage goes from 47 to 74%. So that's a pretty substantial improvement by cutting the wind uncertainty in half in this case. Okay, let's look at another example where we have the same starting point, that same 47% hit probability at 1,000, but now instead of changing the wind, we're going to change our group size. All right, we're originally modeling a 1 MOA group, and this is at 100 yards. Okay, what is your average group size at 100? That's your mechanical precision. So if you go from a 1 minute gun to a half-minute gun, right? Lots of people work hard to go from 1 minute to half-minute groups, assumably because it has a big effect on long-range results, right? Well, in this case, going from a 1 minute to a half-minute gun improved your hit percentage from 47 to 50%. Okay, only 3% improvement compared to cutting your wind uncertainty in half, which took you from 47 all the way up to 74%. All right, so the reason I chose this as an example is because it cuts directly at assumptions that many long-range shooters make, which is the precision of the rifle is of paramount importance, and so I've got to spend a lot of time to shoot the smallest groups possible. In some cases, all that effort doesn't get you as much return on hit percentage as other things like, for example, learning to reduce your wind uncertainty. Reducing the wind uncertainty had a far bigger impact than reducing group size, but many shooters think it's the other way around based on how their time is spent, trying to make small groups all the time. So that's been just one example to show you the kind of analysis that you can do to see how different things will affect your hit percentage. You can do the same thing with muzzle velocity SD, BCSD, atmospherics, anything that you use as an input into your ballistic solver that could have uncertainty. Those are the inputs to the WEZ side of the calculation, because those uncertainties are going to drive what your hit percentage is. And a cool thing about the WEZ is that it's not like a blanket static answer, like your percentage of hit at 1,000 yards is always this. It depends on the uncertainties of the day, which experienced long-range shooters know that's the case. Your chance of hitting a target on a windy day, or a day that's you've got passing clouds and the light is changing and thick mirage, just some days are harder to hit targets than others. And by using the WEZ analysis, you can quantify how much harder the targets are to hit from one shooting session to another. And you learn what variables have the most impact in each specific shooting scenario. Take subsonic, for example. A subsonic long-range kind of shot, 300-400 yards, that's not going to be, you'll see through WEZ that your hit percentage doesn't change very much if you have, for example, a large variation in bullet drag. Okay, a large variation in bullet drag will significantly affect your hit percentage when you're shooting supersonic muzzle velocity rounds, but subsonic muzzle velocity rounds are far less sensitive to changes in drag. So that's one difference that you'll see is subsonic to super, the drag variation isn't as important. And there's just lots of things like that you'll pick up that will inform your insight along the way of doing WEZ analysis. You can also use WEZ. Another example or application would be, say a new cartridge comes out, a new cartridge shooting X bullets at whatever velocity. And everyone's like, wow, this is the new best long-range cartridge. And you can put that in a WEZ analysis and compare it to what everybody's already shooting and see, is this really a world changer, or are we talking about 1 or 2% difference in actual hit percentage whenever you look at the overall performance? So that's a good segue into the part where we're talking about using WEZ to compare ballistic performance, okay? Traditionally, ballistic performance is compared by, drop. Does this round have more or less drop than what you're comparing to, more or less wind drift than you're comparing to? And we just kind of assume that the rounds that have less drop and less wind drift are the higher performance rounds that'll give you better hit percentage, but it's never a direct calculation. WEZ is the direct calculation of how ballistic performance translates into hit percentage in very specific scenarios. All right, so you can really do fine-tuned performance analysis using WEZ. WEZ lets you answer questions like, what's better in the wind? A light, fast, low BC bullet, or a heavy, slow, high BC bullet? Traditional ballistic solvers will just tell you which has more or less wind drift, but WEZ will put that wind drift into hit percentage terms based on how much wind uncertainty you have in a given shooting situation. So it really gets down to what matters and what doesn't. And you know, sometimes a difference in performance exists, but you can use WEZ to put it into context to see, is it a 20% difference or is it a 2% difference? You know, better's better, but sometimes you'd work harder for that 20% than you would for the 2%. Or maybe you'd choose to spend your money on equipment that addresses the 20% error and not the 2% error. So it really just helps you understand the proportions of where your efforts are going to have the most impact. So if you remember anything at all from this video about what WEZ is, it should be this. Okay, WEZ it's the completion of a fire solution. Okay, traditionally we just get elevation and windage from a fire solution, and we get elevation and windage whether we're shooting 200 yards or 2,000 yards. It says nothing about how likely we are to be able to actually hit a target. That's what the WEZ component does. It tells us the likelihood of hitting a target with the elevation and windage that the ballistic solver tells us. Okay, that's the big takeaway, is it's the completion of our fire solution to include the confidence that we should have in the shot. Okay, so you know how normally when you're using a ballistic solver, you're putting in, say, for example, your average muzzle velocity, okay? And it's very important that that's actually your true average muzzle velocity, or else your solution will be off. Got it. All right, well, what you're putting into the WEZ as inputs are the uncertainties of those things. So if your average muzzle velocity is 3,000 feet per second, you put that in to get the elevation and windage side. But to get your hit percentage, in order to understand how much variation you have in velocity, you put in your SD into the WEZ side, okay? And that's in fact what all of the WEZ inputs are, is standard deviations. And that's an important thing to understand, or else you'll be completely misrepresenting your hit percentage. All right, so since that's such an important part, we're going to go into that next. So understanding the WEZ inputs begins with understanding the bell curve. All right, the bell curve, I think everyone knows about it in theory, at least in principle, but what it is, it's a frequency distribution curve. The peak of the bell curve represents the average, and it's the highest because that's where that number will most frequently occur in a normally distributed amount of shots. So if your average is 3,000 feet per second, that's represented by the peak of the bell curve. And then velocities farther from 3,000 feet per second are less likely. That's why the bell curve is lower, far from the peak. Those outliers are less likely. That's what it's representing. So whenever the software is running a WEZ solution and it's pulling from the uncertainties that you tell it, it's clustering most of them around the average and fewer of them far from the average. So that's the idea with standard deviations. Standard deviations define the bell curve. Within that bell curve, we can see by the shaded area that 67% of that area is represented by plus or minus 1 standard deviation from the average. And if you go plus or minus 2 standard deviations from the average, you're capturing 95% of the shots. So if you want to know what the bracket is, where 95% of your muzzle velocities will be, your wind calls will be, whatever it is that we're characterizing in WEZ, 95% is represented by plus or minus 2 standard deviations. So if you wanted to represent an extreme spread in muzzle velocity of 40 feet per second, your standard deviation would be 10, right? Because plus or minus 2 of those gives you plus or minus 20, and that's plus or minus, well, it's 40 feet per second as an extreme spread. So that's what you have to understand in order to properly give the WEZ side of the solver the right inputs. And the same thing applies for wind speed. You know, notice how nothing about the bell curve changed, just the numbers that it represents are now wind speed rather than muzzle velocity. So if your average is 10 miles an hour wind and your standard deviation is 1, that's representing a 4 mile per hour bracket from 8 to 12, right? Plus or minus 2 standard deviations of 1 mile per hour each, plus or minus 2 miles an hour. So that's how you got to think of all these WEZ inputs. If you want to represent a range uncertainty of, you know, a bracket, I think I'm plus or minus 10 meters because I'm milling the target and it's 600 or whatever. You know, plus or minus 10 meters, if that's 95%, your standard deviation in that case would be 5, because that's 10 is 2 times 5. So you want the 95% bracket. So one way to simplify this is if it's more natural for you to think in terms of the bracket, like I think I'll have a 4 mile an hour bracket on calling wind, you can start there and just divide that bracket by 4. And that's going to be the standard deviation that you type into the input of AB quantum to get your WEZ. Here's an example with range showing that you've got a 600 meter average range and a standard deviation of 10 meters. So, it goes plus or minus 2 standard deviations from that. And back to the wind for a second, because this is such an important thing to characterize accurately. The wind speed, okay, and that uncertainty box, once again, you're just putting in the standard deviation of the wind's uncertainty. It doesn't matter if the wind is 50 miles an hour or 5 miles an hour. If you have the same uncertainty of 2 miles an hour, then that's what you'd put in. It's not, the WEZ doesn't care about how high the wind is. It just cares about the variation and how uncertain you are about it. If it's 50 and you know it's exactly 50 and it's not changing, your uncertainty is 0. You can shoot a good group in high wind if it's constant. So that's the idea there. You're just characterizing the uncertainty, not the average with WEZ. So there's actually a lot of inputs to the WEZ side of the solver that characterizes your hit percentage, but a lot of them are related to your instruments, like the uncertainty of the temperature, the pressure, and the humidity. That's really just the uncertainty of your kestrel or whatever you're measuring it with. And they're usually pretty small and less consequential uncertainties. The big ones, your big field uncertainties, are going to be wind, range, muzzle velocity, and your rifle's precision, your grouping. And we have built within AB Quantum sets of predefined or pre-canned inputs to the WEZ solver that represent what we feel are high, medium, and low confidence environments. All right, for example, a high confidence environment, your wind estimation is, we think you're within plus or minus 1 mile an hour. Okay, so a 2 mile an hour bracket. That's like an elite wind reader in a pretty easy wind condition is usually going to have it within plus or minus 1 mile an hour. So in WEZ, your input would be 0.5 for the standard deviation. Your range estimation, if it's plus or minus 1 yard, again, that's going to go in WEZ as a 0.5 yards input to represent that plus or minus 1. Rifle precision, you just input that directly. There's no standard deviation. We do that behind the scenes. So the rifle precision is your average group size, your average 5-shot group size. Okay, most people shoot 5 shots. And then velocity consistency, that's your SD, a muzzle velocity. That's probably the most natural thing. Most people will think of muzzle velocity SD, have no problem. It comes right off the chronograph. But like your wind estimation SD sounds really weird and people aren't used to it yet, but it's the same thing. You're characterizing the bell curve of uncertainty for each of these variables. All right, and then you can see what variables assigned to medium and low confidence environments. It's just, whether your rifle shoots 1.5 minutes or that represents shooting off an unsteady support, plus or minus 50 yards range, that's like relatively poor milling. You don't even have a rangefinder. So low confidence really is representing, and you see it in your hit percentage too. Like your hit percentage for the low confidence environment is much lower than it is for the high confidence environment. So if you want to compare apples to apples over time or with different people, you could use those pre-canned selections that automatically characterize all your uncertainties. That's the easy button. But if you know that your uncertainties are different and you want to really get down to modeling your specific shooting, you can go in and change all of these to whatever you want. Okay, getting to the fun part now, how the implementation of WEZ into AB Quantum. All right, so there's several ways that you can look at the output. The first thing that's most natural that we've been looking at is the shot simulation. Okay, that's showing you the scatter plot, you could think of it, in relation to your target size. That alone is very informing, just to show you how big your group is in relation to your target. Another type of output you get is a breakdown of the components that are driving your uncertainty. All right, so in other words, it's showing you what's most consequential to you driving your group size in the vertical direction or the horizontal direction. So in this example, it's showing you that most of your vertical dispersion is coming from muzzle velocity. Like if you wanted to improve your hit percentage by reducing your vertical, muzzle velocity is the biggest thing to work on. It wouldn't make sense to work on, getting your range uncertainty down, because that's not what's driving your misses here. And then you got the same thing in horizontal, where the story of that is almost always going to be that wind is your biggest variable in horizontal uncertainty, with the rifle group being the second. You can also look at your WEZ as a function of range to see, like in this example, your hit percentage is 100% until around 800 meters, and then it starts to fall off. So that's just showing it to you by range. It's basically a scatter plot at every range and then looking at that percentage. So we've talked about the inputs of the WEZ analysis in terms of like, your muzzle velocity SD, your wind uncertainty, and those inputs. Another really important input to the WEZ is your target selection. That happens to matter in hit percentage calculation. So a big target, obviously, you'll have a higher hit percentage against than a smaller target. We have a few common things represented here. We've got IPSCs. You can define rectangles of different sizes, circles of different sizes, deer, elk, coyote, prairie dog. Those are our other targets that we have for now. Just to show you a comparison of hit percentage for different targets, we've got this scenario that's giving us a 76% hit probability against an IPSC target at 1,000 yards, but whenever the target is a coyote, the hit probability is down to 5%. And it's probably far less than that because WEZ doesn't account for moving targets and coyotes are always moving, it seems like. And so, that's just the difference in target changes your hit percentage from 5 to 76%, which is very natural. Anybody with experience knows the target matters, how big or small it is as far as how easy it is to hit. But again, WEZ is what's putting a number on that. Like you can look at these, I call them waterfall plots of the WEZ showing, against the IPSC, the plot is very full, 100% for a long way. But against the coyote, you fall off 100%, looks like right after 300 yards, and then it drops steeply, and you're below 50% before 600 yards. So that's the kind of information that you're getting from a WEZ analysis whenever you're looking at these waterfall plots. All right, so up until now, I feel like we've been covering WEZ, talking about it and describing it, how to use it and everything. There's a few, advanced tips that I want to give you about WEZ that'll help you be a more savvy user and understand how to get more accuracy out of your analysis. One of the input fields that you have to work with is the drag uncertainty of your bullets. Now, most shooters don't know what that's going to be. You would have to do a measurement of some kind with a radar and, get what that is. But I can tell you, based on all the testing that we've done, that bullets that are considered really good for long-range shooting have standard deviations of 1% or less in their drag. So that's what you're going to want to use for bullets like that. Bullets that are, not typically used for long range, but can be, or bullets that are, I'd say, kind of poor for long range shooting, 1 to 2%, not poor, but more average. And then if you get bullets that are poor at long range, they give you big vertical dispersion, maybe have stability issues, you'd want to model a 3% or more for bullets like that. So it's usually going to be a 1, 2, or a 3% in that field. To help you get good results. There's also a handful of inputs for environmentals, temperature, pressure, humidity, and those things, whatever you're measuring environmentals with, usually will have published specs that tell you what its accuracy is of the different measurements, and that's what you can put right in there. If you're measuring with something, if you're getting within 2 or 3 degrees of temperature and so forth, then it's probably not driving your hit percentage, these uncertainties. But if you want to really put in the right numbers, they're published by whoever made your instruments. And then another tip, I don't know if this even qualifies as a tip or if this should be in the basic user manual of understanding what WEZ is doing for you. But it's really important to understand the difference between a WEZ for a first shot versus the WEZ for follow-up shots. All right, so think about it. When you're identifying your wind uncertainty, let's say you give it a 2 mile an hour SD, which is going to represent an 8 mile an hour window. Maybe you can only call the wind within plus or minus 4 miles an hour, like a lot of shooters, and that's okay. Put in your 2 mile an hour SD, and now whenever you shoot at your target, you take your first shot. Suppose you hit 1/2 mil right. If you're like me, I'm going to send a quick follow-up holding 1/2 mil left. And if you think about what you're actually doing there is you're taking that initial wind uncertainty, you were somewhere in this 4 mile an hour bracket. Well, as soon as I saw my shot hit 1/2 mil right and apply a 1/2 mil left hold, I'm essentially, if I shoot quickly, a quick follow-up, I'm essentially taking my wind bracket to 0. I've eliminated, because I saw where I hit and I'm applying a correction. So my second shot doesn't have the same hit probability as my first shot did because I'm using information from my first shot to narrow the uncertainty. So my second shot will have a very different WEZ solution than a first shot if you see and apply the feedback. Now, if you never see where you're hitting and just keep sending shots, that's going to represent your WEZ, as it was originally calculated. But anytime you're incorporating feedback in your follow-up shots, your WEZ calculation actually should go up dramatically, because like your range or your wind uncertainty, whatever you had uncertainty about before you shot the first shot, you're getting a lot of information that'll help you narrow those bounds. Okay, so we'll do a quick summary of all the features and facets of WEZ. Basically what WEZ is doing, it stands for Weapon Employment Zone, and it's calculating your hit percentage. Okay, and it's doing that by modeling the dispersion of your group in relation to the target in the specific field conditions that you identify. Okay, that's what it's doing, and that's what it's giving you. Now, what you can use that for, there's a lot of things you can use that for. You can use that to identify what the dominant variable is that's driving your dispersion both in vertical and in horizontal. So if you want to ask the question, what can I do to improve my hit percentage? WEZ answers that question directly by showing you the variables that are hurting your hit percentage the most. All right, so that's a great thing it can do, is identify the variable that is holding you back on hit percentage the most. Another thing it can do is you can compare ballistic performance in the same set of field uncertainties, right? Like if you have, what you'll find is that in a high confidence environment, you will be able to see the difference, a small difference in ballistic performance will show up as a difference in hit percentage if you're in a high confidence environment. But if you're in a low confidence environment, a small difference in ballistic performance doesn't necessarily translate into higher hit percentage, because the effect of those variables overwhelm it. So these are all things that, again, it's like experienced shooters have an insight for this, but you need WEZ to actually put the number on it, okay, and not be misled. Some of our insight isn't right, and WEZ is what will help us straighten that out. You know, if you're a long-range hunter and you want to identify a specific, WEZ criteria that you won't shoot at your game animal outside of a WEZ that gives you, for example, 95 or 80%, whatever your threshold is for, certainty on a shot against an animal, you can actually calculate that and have that as a number rather than rely on gut instinct. And I'll close by saying that, WEZ is, it's a component of a complete fire solution, all right? And really, we should have had WEZ all along. Something to tell us what the confidence of our shot is. Having a windage and elevation solution is great, but when it says like 253.25 minutes of angle, something with that solution should be telling you it's a low probability of hitting that target. And WEZ is what does that. It's time, it's 2025. There were reasons WEZ didn't make its way into field calculations sooner. Part of it is because, of the additional computational requirements. Chips weren't always fast enough, whatever, but now, again, it's 2025, chips are fast enough to run WEZ in the field, so we instantiated the software that'll do that for you, and now you have complete fire solutions giving you not only windage and elevation, but also telling you what your chances are of hitting a target at any range, and that's what WEZ is all about. So thanks for watching. There's more on this topic in the links in our description, and if you want to be informed of future instructional videos coming out, you can subscribe to this channel to be notified.